So now that you guys understand that problem, do you want me to give you another one of those? No? You're good? All right, well, I will cease and desist then from scratching that itch. Now, so next up, continuing our discussion of frames, there's an interesting, and this, okay, so here is where we have decidedly left the world of Calculus 3. Everything I was saying right up till before the break is something I would teach in Calculus 3. You know, I was a double major in physics and mathematics, and in my physics, I learned this wonderful world of parameterized Calculus 3. All the definitions that I saw in physics for vectors, for line integrals, for surface integrals, these were all given in terms of parameterizations, really. And the examples were all written in terms of the cylindrical and spherical coordinate frames. And then I would go back and look at the usual calculus books, and they're nowhere to be found, and it's sad. So Calculus 3 books tend to be written in terms of Cartesian coordinates, and they're very, they shy away from really embracing the full glory of the parametric viewpoint. And they certainly don't do justice to the geometric viewpoint, which is popular in physics. So, I don't know, if you look at my Calculus 3 notes, I actually try to bridge the gap between these two worlds of how to look at Calc 3. That doesn't have too much to do with here, but whenever I talk about r hat, theta hat, z hat, phi hat, it makes me think of that. Anyway, so if we have a frame, we can define something called the attitude of a frame. In particular, it's a matrix. The attitude of a frame is a matrix, and that matrix corresponds in a one-to-one way with the frame, because it has all the components to the frame. And so this is definitely not something I would do in Calc 3, right? You did not see this in Calculus 3. In fact, I very strongly doubt you've seen this in any other course. The only place I've ever seen this is O'Neill. All right? But it is a standard thing. And so what's going on here is we're peeling off the components with respect to the standard frame and putting them in a matrix. But the components aren't put in columns, they're put in rows. All right? So, yeah. No? Okay. So, before I even get to the theorem, the first theorem about this, let me just give you an example. For U1, U2, U3, we get A equal to the identity matrix. All right, because, for example, U1 is equal to 1 times U1 plus 0 times U2 plus 0 times U3, right? So that 1, 0, 0 appears here. Similarly, U2 is 0, U1 plus 1, U2 plus 0, U3. So we get 0, 1, 0 for the middle row, and so forth for U3. What's the attitude matrix for the cylindrical coordinate frame? For E1 equals to r hat, E2 equals to theta hat, E3 equals to z hat, we get the attitude matrix of what? So you can read it off the other board, right? You know, you look over here, you go, oh, so for E1, the first row of my attitude matrix, I've got cosine theta, sine theta, 0. The second one, I've got minus sine theta, cosine theta, 0. For the third one, I got 0, 0, 1. There you go. That's the attitude matrix for the cylindrical frame. Right? Cylindrical, yeah. And of course, we could do the spherical frame. I mean, you want me to, right? So for the spherical frame, E3 is rho hat. Rather, E1 is rho hat. I'm an idiot. E2 is phi hat. E3, theta hat. With the usual math convention, not O'Neill's convention, by the way, we get A equal to, well, I can tell you the last row is minus sine theta, cosine theta, 0. The first row is, oh, I should space those out more. Good grief. The first one is cosine theta, sine phi, then sine theta, sine phi, then cosine phi over here. The middle row, I can't ever remember, but if we worked out the signs right last time, hopefully I'm right, cosine theta, cosine phi. I'm about 90% sure on the signs on the middle row here, cosine theta, cosine phi. I mean, we did calculate dot products and got 0 for both of those. That's if we're wrong on E2, we're very unlucky. Sine theta, cosine phi. And minus sine theta, or minus sine phi, rather. Yeah, okay. Great. So these are the attitude matrices for each of these frames. And what can we say about this attitude matrix? Definition, if A in Rn by n has A transpose A equal to the identity, then A is an element of On, which is to say A is an orthogonal matrix. Orthogonal matrices satisfy this condition that A transpose A equals to the identity. I have a lot more to say about this in chapter 3. I'm just kind of throwing it out there as a definition at the moment. I'll motivate it later. There's a good motivation for this definition. But here's the interesting thing, is that the attitude matrix is an orthogonal matrix. Theorem, attitude matrix. Of frame is orthogonal matrix. And so here's the proof of that. So if we look at A transpose A and look at the ijth component of that, so if you haven't had linear algebra, I'm sorry at the moment. Like, I have to just quote something we learned there, which is how to multiply matrices. The formula for the ijth component of the product of two matrices is the sum over k of A transpose ik a k j. This is matrix multiplication in index notation. Now, the transpose of a matrix does what? It flips the row in the column. So A transpose ik is actually aki akj. So that's literally equal to that. But how did we define the attitude matrix? What was it? What's AKI? It was, let's see here, so Aij is EI dot EJ, so this would be EK dot EI. Well, not EI, UI, right? So the attitude matrix somehow captures how the perhaps non-standard frame relates to the standard frame. It somehow captures how the non-standard frame has been twisted from the original frame. We could think of it that way. Now, what's this we're looking at here? Okay, so what do we do next? So now you got to use your imagination a little bit. What is this? This is the kth component of UI with respect to what? The E1, E2, E3 frame. Do you see that? If I take the vector UI and I dot product with UK, that picks off the kth component in the E1, E2, E3 frame. And by the same token, this is the kth what? A kth component of UJ, right? With respect to the frame. Let's call it the E frame. So remember that theorem we had and I just erased? The dot product in the other frame is equal to what? The sum over matching components in the E frame. So we have k component of UI, k component of UJ summed over k. This is exactly the dot product of UI with UJ. I'm an idiot. Let me write that down. So that's UI dot UJ by the theorem that I had a little bit earlier. And what is UI dot UJ? That's funny. When I wrote the proof in the notes, I came out to the conclusion EI dot EJ there. Oh, I could see that too. You could go either way, right? You could go either way. Like, this is one way you could go. Well, no, I think I got to go this way. I think the notes are wrong. So this is Kronecker delta ij, right? And I don't know if you knew this or not, but that's a formula for the ijth component of the identity matrix. The Kronecker delta is the identity matrix formula in components. And since this calculation holds for all I and j, it follows then what? Therefore, A transpose A is equal to the identity, which goes to show you that, indeed, it's an orthogonal matrix. Orthogonal matrices are kind of cool. Notice something. What's the inverse of an orthogonal matrix? BTW. It wouldn't be the what? Determinant with all. Well, just look at this formula. A transpose A equals to I, right? So what is A inverse equal to? A transpose, right? Which is super nice because inverting a matrix is generally a pain, but transposing a matrix is easy. So allegedly, the inverse of these matrices is just formed by transposing. But you could try multiplying this any one of these matrices times its transpose. You should get back to the identity matrix. That's what this theorem proves. Now, I think that on its lonesome isn't especially interesting, but what we'll do with it before long will be interesting. So that brings us to section 2.3, which is on the calculus of vector fields along curves. All right. By the way, it won't be long, and we'll be doing things like taking the exterior derivative of these matrices. Like we'll calculate dA, where we take the differential of each one of the functions, and we get a matrix of differentials. And then we do stuff with those that's related to like the shape of the surface and such. It'll be a minute or two before we get back to that, what I just said, that calculation I just talked about. It's like a little bit later in the course, but not too long. Section 2.3. So here we want to talk again about a smooth parametrized curve. Oh, thank you. I think the longer I get into the lecture, the worse it gets, right? Smooth parametrized curve. All right, and let's let y equal to sum over I of y upper I partial I. All right, smooth vector field. On the curve. And so you might wonder what I mean by smooth vector field on the curve. That probably needs to mean that the functions which define the vector field are smooth pretty near to the curve. In other words, when I evaluate the vector field on the curve, I get smooth functions. So,
is that differential I? Differential I or alpha?
Oh, partial I. This is an abbreviation for partial xi, if I wanted to be more, verbose. Then we say y is an element, and this is kind of a funny symbol, guys, but basically it's like two parentheses back to back with a cross through them. So that's my notation for vector fields on the curve. That is x with a cross through at alpha is the set of smooth vector fields on alpha. The functions y sub I are the Cartesian coordinate functions of y. So these guys, y1, y2, y3 are Cartesian coordinate functions of I. I should say of y. I said I meant y. In contrast, y1 composed with alpha, y2 composed with alpha, y3 composed with alpha are the parametrized components of y along alpha. And we say y is smooth to say it has smooth coordinate functions, all right? You say where? I would say it has to be true on some open set which contains the curve's image, probably for this all to make sense. So I give an example. It's probably worth us looking at the example, right? This definition, I think, is easy enough to misunderstand, so let's try to understand it. How about alpha of t equals to t squared, t cubed, all right? And I'll look at the vector field y equal to, let's do something funny, z cubed partial x plus y squared partial y plus x partial z. I'm ignoring the notes, all right? I made up a new one. So what are the Cartesian coordinate functions of y are what? So like y1 is z cubed, right? y2, yeah, y squared, y3, x, right? What are the parametrized components of y with respect to alpha? So if I calculate y composed with alpha of t, what do I get? I get, what is my, so I get, oh, goodness gracious, t cubed cubed, partial x plus t squared squared, partial y plus t, partial z, right? And to be clear, the partial derivatives are all where? Evaluated where? At t. Right idea, but I would say alpha of t, right? Because z, the z component for the curve is t cubed. So I have to plug that in there and then cube it. Now, so now we can define the change in a vector field along a parametrized curve. So, let alpha be as above. Let's let y be an element of x of alpha again, like it just was, all right? Then derivative of y along alpha is y prime of t. And what that's going to be is the sum, I equals 1 to 3 in our case, d of y I composed with alpha dt times partial x upper I evaluated, of course, at alpha of t. And for what it's worth, that's an element of the tangent space to alpha of t of R3, at alpha of t of R3. So I think the equation I have right under the definition is like super helpful. So just for example, if y of alpha of t is equal to au1 plus bu2 plus cu3, where a, b, and c are functions of time, right? In fact, a, b, and c are what? They're the what I just talked about up here. They're the parametrized components of y with respect along alpha, right? Then y prime of t is just au1 plus b, oh, excuse me, dA dt, u1 plus dB dt. Sorry, my font has gotten messed up. dA dt, u1 plus dB dt, u2 plus dC dt, u3. So let's see here. I guess we could calculate the change of, and based on the example I have right above the definition, we could try to calculate the change in Well, we could calculate the derivative of y along that alpha, right? What would it be? Yeah, what would y prime of t be here?
The first one would be 1. No, y prime of
This is t to the 9th, right?
9.
This is t to the 4th. So you said 9,
Yeah, 9t8.
yeah, 9t to the 8th power partial x, right?
4t cubed partial y.
Mm-hmm.
And then partial z.
Partial z, right. Of course, we could go back to the u1, u2, u3 notation if you want, but now, this notation will sneak up on you and bite you later chapters if you don't know what it means. This is a very kind of dangerous notation. Why is this a dangerous notation, by the way? I think it's a dangerous notation.
The prime.
The prime notation. Like, what is it?
It's technically y. That's y composed of alpha prime.
Right, it's y composed with alpha prime. That's essentially the I mean, to me, there's a danger here. It omits the explicit mention of the curve. And if you're not aware that there's a curve dependence, you kind of like go, what? How does that make sense? Because you can't just differentiate. You know, if I gave you this, right, and I said calculate y prime, you'd be like, but how would I calculate y prime just with y alone without the alpha, you know? So, anyway. But if we have a parameterized curve, then we can calculate the rate of change of the vector field along the curve. And, let's see here, where did I go? And there are nice properties to such derivatives, right? So, theorem for y and z smooth vector fields along a curve alpha, and C1 and C2 in the reals, we have the derivative of C1y plus C2z. And now, see, now I'm committing full bore to the prime. I switch the prime to ddt, right? So, okay, fine. I mean, really, we're just omitting a composition with alpha in some sense here, right? So it's not like that bad a notation, but. So we have linearity. We have, now this one's important. And this one might surprise you a little bit, I don't know. But if you have the derivative of the dot product of two vector fields, which is something we can define, right? And for some reason, I put alpha of t here. Like all of a sudden, I'm writing alpha of t. I'm not going to write that, though, because we haven't written it anywhere else. So I'm just going to write it down like this. But you should understand what this means is at alpha of t, right? So we have a product rule for dot products, and we also have a product rule for cross products. And you got to be careful with the cross product because it's not commutative. So you have to maintain the order of the cross product. Otherwise, you will be incorrect. But there you go. The proof of those is pretty straightforward. Basically, you just write down the formulas in terms of the parameterized components. You take the derivative, and by the usual rules of calculus, you get the result. So like item number 1 is true because that's a rule for derivatives. item number 2 is true is because there's a product rule, and the product rule plays nice with the formula for the dot product. Proposition number 3 here is true because there's a product rule, and it plays nice with the cross product. All right. I have an explicit proof of part 2 in the notes. I say I've left 1 and 3 to the reader. Those might actually make decent homework problems. If I do make that a homework problem, I think like the smart way to work it is using that epsilon ijk notation. Well, anyway. So now we have a way to define, we've defined velocity to a curve, right? And now we can define, it's not a word. Do you remember how did we define the velocity to a curve? How do we do that? Take the derivative. That sounds right. Let me see here. If I recall correctly, definition. So if alpha goes from I, subset of the reals, to R3, smooth parametrized curve, then alpha prime of t was equal to a sum I equals 1 to 3 of d alpha upper I dt partial x upper I at alpha of t, which of course in the usual notation is just the usual thing, right? It's d alpha 1 dt u1 plus d alpha 2 dt u2 plus d alpha 3 dt u3. This is the velocity. We just differentiate the components, you know? Well, what's new now is we can define the acceleration of a curve. Definition. Alpha I to R3 as above, smooth parametrized curve. Then alpha prime prime of t is equal to d dt of alpha prime of t. And now I think that's a little bit of a cheat. Because there's not necessarily a Cartesian vector field y where these component functions are coming from, all right? So this really is a definition. It's not piggybacking up top of that other thing. It's reasonable in view of that, but anyway, here it is. This is equal to the sum. Of course, what I'm about to write down is nothing more than Calc 3, really. T squared alpha t squared partial xi at alpha t. Right, and this is an element of the tangent space at alpha t of R3. So for the running example we have, we had alpha of t, what was it? T squared, t cubed, wasn't it? So alpha prime of t, 1, 2t, 3t squared. Alpha prime of t, 0, 2, 6t. Or in our other notation, of course, this would be partial x plus 2t partial y plus 3t squared partial z. And these are all at what? Alpha of t. So you can see why you can see why he likes to write like 2u2 plus 6t u3 here. Because writing 2 partial x2 at alpha of t plus 6t partial x3 at alpha of t, it's kind of obnoxious. I mean, it does say exactly what's going on, but it comes at the cost of a lot of writing, right? And now we reach the final theorem for today. So I mentioned at the top of page 35 that we can talk about distant parallelism in Rn, right? What does it mean for two different vectors in Rn to be distantly parallel? I mean, it means that basically they're attached at different points, but they both point in the same direction. You know, this is distantly parallel. So we use distant parallelism all the time to move vectors around in Rn, right? This is parallel transport, right? I can attach this vector here like so, or I can attach it over here like so. Those vectors are distantly parallel. They have the same direction, they're just attached at different points. All right? So I'm not sure why I'm talking about that here, actually. Man. I mean, I like that paragraph. I just don't know if that's where it belongs in the notes. Anyway, here's the theorem I mentioned. And after the theorem comes us leaving, which is, you know, desirable, right? So theorem 2.3.8. It says let alpha to R3 be a smooth parametrized curve number one, alpha prime equals to 0 if and only if alpha of t is equal to p for all t and I. 2, alpha prime prime is equal to 0 if and only if alpha of t is equal to p plus tv for all t and I. 3, let y be a smooth vector field along the curve alpha. Then the derivative of y along alpha, in other words, y prime of t is equal to 0 for all t and I, if and only if y composed with alpha is constant. This one, it says alpha prime prime is equal to 0. Like this last one, you could also replace this whole jibber jabber here with y prime equals to 0. Now, you guys, before we prove this, what is item 1? What does that say about alpha? Alpha's constant. It's equal to the constant. It's always going to point P, right? So that's that stupid curve beta we saw earlier today. It's not really a curve. It's always going to the point P, right? It's a point. Alpha's a point. What's the second one say? Right, that's a line. So the acceleration is 0 along the curve if and only if it's a line. And the derivative, the change of a vector field along a curve is 0 only if the parametrized components of the vector field are constants. Yeah, I think 3 is the one that we'd have to think harder about to understand more.
So you said the change in the vector field can only happen if they change the constants and the components?
So let's see here, y prime equal to 0, right? That means that,
Yeah, that means that when that has to be a constant.
yeah, so let's suppose y composed with alpha is equal to a u1 plus b u2 plus c u3, right? Then dy dt, is equal to dA dt, dB dt, dC dt, right? Now, if this is y prime by definition, so if this is equal to 0, what's that mean? It means dA dt equal to 0, dB dt equal to 0, dC dt is equal to 0. But that implies what? Provided that the domain of the curve is connected, it implies it's a constant. If your domain had disconnected pieces, you could have different constants on the different pieces and still have 0 derivative throughout. It's important that the domain of the curve be connected. But so A is equal to C1, B is equal to C2, C is equal to C3. I'll put the upper indices to make it look the same, which is the claim, right? So that's the forward implication of that proof. In the reverse implication, it's almost the same. If you have that those are constants, if you differentiate this, constants differentiate to 0, so we get y prime is 0. And the proof of part 1 and 2 is very similar. But take a step back here and appreciate what's just gone on. We have characterized what it means to be a point and what it means to be a line in terms of calculus.
But this is still for R3.
Still for R3. Yeah, this is for R3, but I think that that's just kind of window dressing, right? I mean, is there anything inherently three-dimensional about what's going on? We could make this same theorem in Rn if you wanted to. So that's a good place for us to stop today. Next time, we will talk about the Frenet-Serre equations and move along. I think I need to fix my course planner. Now it's hopelessly wrong. I'll have to change it. I don't think it's going to move much around. Just I'll have to fix it. Listen.